Alrighty, hi everyone. Welcome to your review session. It's 1 o'clock, so we'll get started. Again, this is just going to be an hour session and a place where you can ask any of your last minute questions before your exam, either Monday or Tuesday, depending on if you have Dr. Altimos or Dr. Altman. And then if you are here and want to watch this later, this is being recorded and will be posted after we're all done here. So this should be up before 3 o'clock, I'm hoping. Alrighty, so with that, I'll open the chat, or you can just take yourself off of mute, and you can go ahead and ask any questions you may have. This can be about anything that you might have a question on. Format of the exam, a question from a mock exam, a topic in general. This hour is for you.
Can you go over number 10 on the mock exam?
What class do you have?
I have Altimos.
Alrighty, so I think I have this one. All right, so this one here, butyl acetate.
Yes.
Awesome. So this question says butyl acetate is a compound containing CHNO and occurs naturally in many fruits. The synthetic form of is used to impart fruity flavors into candy, ice cream, and other sweets. It is found to be 62.1% carbon, 10.3% hydrogen, with oxygen making up the remainder. Determine the molecular formula of butyl acetate, given that its molar mass is about 116 grams per mole. So what like, I guess, broad general topic is this question asking about? What do we usually, like, what's the basis for this question?
Are you asking
percent competition?
Yeah, percent composition is perfect. Great. And then we could also maybe call this one like an empirical formula type of question as well. Okay, so I always like to ask myself that question when I start one. Is like, okay, what is this asking me? What topic is this from? Because then I can kind of switch my gears in my head to say, okay, this is what I usually know about that topic. And then that helps me proceed with the question. So the best thing that we know is that CH and O make up the entirety of the compound. We know that carbon is 62%, 0.1%. Hydrogen is 10.3%. So what does that make oxygen?
27.6%.
Yep. Right. So we know the percent composition of our elements in our compound. When we're talking about this type of question where we're trying to find the molecular formula or the empirical formula, we could always assume that we have 100 grams of this, because then all of our percents go directly to grams of the element that we have. Okay, so now if we added this up based off of grams and percent mass, we would see that we still get 62.1%, 10.3%, and 27.6%. Okay. Do we like to work in grams, or do we like to work in a different type of unit?
Convert it to moles.
Good. We always have to convert it to moles. So we'll do that for each one of our compounds. So now we're in moles of all of our compounds. What do we do once we're in moles of everything?
Divide by the smallest.
Yes, yep. So which one's our smallest here?
Oxygen.
Yep. So then for carbon, we get 3 hydrogen. We get 9. And then for oxygen, we're gonna get 1. Okay. So what can we do for hydrogen?
Would we round it up to 6?
We would. Yep, this is close enough. You can round it up to 6. So we end up with, if we combine this, C6, oops, sorry, not C6, C3H6O1.
Is there a specific, how close does it have to be so that you can round it up? Is there like a specific amount or?
Yep. So if you see something of like 0.25 or 0.75, this would be the same thing as 1/4 or 3/4. So you can multiply this by 4 in order to get rid of that, order to get rid of that fraction.
I have a question.
Yep.
So are you saying that for number 10, A is correct? Because on the review sheet, it says that B is correct.
No, we haven't finished the question yet.
Oh, okay. Okay. Just
Yep.
making sure.
Yep. So those are 2 decimal points where you would have clear what you would multiply by. 0.5, right, is 1/2. So this would be times 2. And then if you have 0.333 or 0.667, then this would be, right, 1/3 or 2/3. This would be multiplied by 3. Anything else, you can either round up or down depending on where you are in your decimal. So anything like 0.1, 0.2 can probably round down to the nearest whole number, and anything 0.8, 0.9 can round up to the nearest whole number. Anything between 0.25 and then 0.75, you would have something that you could multiply by in order to get it to a whole number. Does that answer that question in terms of rounding?
Yes.
Yep.
Thank you.
Okay. Yep. So back to our question, right? We said that our empirical formula is C3H6O1. We need to determine the molecular formula based off of the molecular weight of this empirical formula here. So in order to find the molecular formula of the empirical formula, we have to write 12.01 times 3, right? Find its molar mass. 6 times 1.01 plus 16.00. And we get 58.09. What we are given that the molar mass of the molecular formula is 116. So we can divide 116 by 58.09. And we end up with 1.99690, which we can round to 2. So we're saying that the empirical formula is 2 times as heavy, or I'm sorry, the molecular formula is 2 times as heavy as the empirical formula. So we need to take our C3H6O1, multiply everything by 2, so we get C6H12O2. And this is now our molecular formula, which makes B correct.
So you just divide what you actually get, or like what it's asking for by what you actually get.
Yes. Yep. So if they told us that our, if they told us that the, oops, sorry. if they said molecular weight or molecular mass, molar mass of molecular formula was 174. Wow. Then we would take 174 divided by 58.09. And this would be about 3. So then this becomes C9H18O3, right? Because you have 3 times as much weight as the empirical formula.
Could we also go over number 2?
Yep. Any other questions on 10 before I move on? Does that answer the question of the person who originally asked that?
Yes, what's the one with the 0.25 and 0.75? I wasn't there for that part. Could you explain a little bit for that for me?
Yep, so that's just if you are given, when you divide by the smallest moles, then you're gonna end up with the decimal in some point, in some cases. So depending on, was a question on how you round or what to know to round to. So if you have any of those decimal points, then you can multiply by 4, 3, or 2 respectively, or 4, 2, or 3 respectively. Anything else you can either round down or round up. But if you're between 0.25 and 0.75, then there's 0.333, 0.667, and 0.5 that you could potentially round, or that you could potentially multiply a whole number to get to.
Okay, thank you.
Yep. Okay, number 2. So for question 2, we have, what is the precipitate for the reaction below? We're given lithium chloride and magnesium nitrate. So the first thing you want to do is you want to predict your products, right? This is a predict the products type of question. What do we call this type of question? Or what do we call this type of reaction?
Is it
It's a
chemical?
double replacement.
Oh, never
Yep.
mind.
It's a double replacement, double displacement, either one of those. Okay, so what do your partners become, or what do their products become? What's one of them?
MgCl.
Anything else with that MgCl?
Put 2 for the Cl. Wait.
Perfect. And what else?
And lithium nitrate.
Okay, so you're given your reactants and then your products. So it's going to be magnesium chloride and lithium nitrate. Do we really care about the balancing of our equations here?
No, I don't think it really matters.
Nope, this one doesn't matter, right? We're just trying to find the precipitate. It doesn't matter if we're balanced or not. You can just look at your magnesium chloride or your lithium nitrate. So if you're asked for a precipitate, what should you look at next?
Solubility table.
Yep, you need your solubility table. So looking at your solubility table, is one of these going to be a solid?
So when you're asked for a precipitate, or is it just asking you like which one is going to be solid if at all?
Yes, yep, they're gonna say which one is going to be solid if there's a solid forming at all. Yep,
Okay.
Both would be aqueous, right?
which one's aqueous?
Both.
Okay, let me look at.
So
Yep, I would agree with that. I would agree that this one would be aqueous and this one would be aqueous. And so what is our answer choice?
no precipitate.
No precipitate is formed. Yep. Right, and so if we're looking at our solubility chart, NO3 minus, these are always soluble. Lithium plus is always soluble. And then chlorine is always soluble. Except, oops. Ag plus, Hg plus 2 plus, and lead 2 plus. Okay, so since chlorine is with magnesium here, that's not one of the pluses that we see in our exception side, so both of them will be aqueous. So no precipitate forms because no solid is forming. Nothing becomes insoluble.
Will we have that table in the exam?
Yeah, so if you're looking at the mock exam, the multiple choice portion of it, that's like what your packet is going to be when you get it. Your answer key, which is that separate document, is what you're actually going to be filling out your answers to, or filling out your answers on. So it'll be the periodic table on one side and then the solubility chart on the other.
I have a question in regards to the wording of like questions like these. So is it is it going to tell us, like, for example, if there's like an acid-base reaction, is it going to tell us if it's like if it's a strong or weak acid, or would we have to or would it give us a table? How would that work?
For this one, they would tell you if it's like an acid base, they would say a strong acid is mixed with a strong base of some sort. Or you'll be given like a titration happens. And so titrations happened with acids and bases. You won't necessarily need to know if it's a strong acid or weak acid, or strong base or weak base in that case. But they would give you all the information you need to know in order to solve the problem correctly.
Okay, thank you.
Yep. Alrighty, so for question 9, we have silver nitrate. Oh, and then Jackson, this is an hour, so it's 1 to 2. So question 9, silver nitrate and aluminum chloride react with each other according to the following balanced equation. It's given below. And what is the mass of silver chloride is produced when so much of silver nitrate reacts with so much of aluminum chloride? All right, so who wants to tell me what kind of question this is?
Limiting reactant.
Good. This is a limiting reactant question. And which one are we being asked to solve for? Like, what product are we looking to solve for?
The silver chloride.
Good. Yep. We're looking for the silver chloride. Okay. They give you the balanced equation below. I would always take 1 minute to check to make sure that it is still balanced. Quickly looking at it, it does. So balanced equation is good. So if we are given the mass of starting material for both of our reactants, what can we do to solve for our limiting reagent? What would we do first?
Convert each to moles.
Good. We need to convert each to moles. So we'll take 4.22 grams of silver nitrate. We're given the molar mass. So we can convert that to moles of AgNO3. Once we get to moles of AgNO3, what can we do from there?
Mole ratios.
Mole ratios. What's going to be our mole ratio?
3 to 3.
Yep. So if you're solving for the limiting reactant in terms of saying how much product can be produced, we can say that 3 moles of AgNO3 is going to be 3 moles of silver chloride. If you check to see between reactants, then your ratio here would be 3 to 1, where 3 moles of AgNO3 is equal to 1 mole of aluminum chloride. Okay. So we would end up with 0.024. Of silver chloride. And we're going to do the same thing for our aluminum chloride. What's going to be our mole ratio here for aluminum chloride? Good. Then we end up with 0.164. 165 moles silver chloride. So which one is our limiting reactant?
Silver nitrate?
Yep, silver nitrate would be our limiting reactant because this produces the least amount of moles. And so we can take those moles that are produced. We can convert that back into grams. So I get 3.55 grams of silver chloride, which is pretty close to B.
Could you do a question like this, but where it asks for the excess reactant, or no, yeah, the excess reactant in grams as well, or
Yep.
would they give us some? Okay.
So if we just take this question, how do we do this? Okay, so if we take this question, right, we know that we produced this many grams. Right, this is how many grams of our precipitate formed. But now I want to ask you, just ignore this a little bit. How much AlCl3 remains? How would we go about solving that?
You would find how much it was actually made and subtracted from how much it would have been made.
Perfect. Yep. So we know that we have 4.22 grams of silver nitrate. Again, we can get to moles of silver nitrate. But instead of doing the molar ratio from reactant to product, we're going to do the molar ratio from reactant to reactant. So for every 3 moles of silver nitrate, we have 1 mole of aluminum chloride. We can then convert that aluminum chloride moles into grams again. So we have 1 mole of aluminum chloride, get us back to grams because we started with grams. And so that's going to be the best way to describe how much is left over. And that is 133. And so we're saying that if we use up all of our 4.22 grams of silver nitrate, which we do because it's our limiting reactant, that means we use 1.104 grams of aluminum chloride used in the reaction. So if that much was used in the reaction, how do we find how much is left over? Or how much remains?
Subtracted from how much there is.
Yep. So we have how much there started with, which was 7.73. We used up 1.104. So we end up with 6.63 grams of aluminum chloride remaining.
Could you also do the same calculation process, but instead of using grams, using the actual moles?
Yeah, absolutely. Yeah,
Okay.
you can totally do this whole thing in moles, right? You don't need to do grams. The question just asked for it in grams. That's why I put it back to grams. But if you're given moles, then that's just one step you don't have to do, because for in grams, our first step is always to convert into moles. So if you're in moles, then you just save a step.
I see. Thank you. Also, in terms of molarity and moles, what would be the hardest question that we're more likely to see?
Probably, like, I think if it's molarity and moles, then I would probably say a limiting reactant question where you're given molarity and volume. Because then you have to multiply your molarity by your volume to get to moles first, and then solve a limiting reactant problem. That I would say would be the hardest.
Right.
Yeah, I would
So
say that.
something along the lines of what we just did right now,
Yeah,
essentially.
I would say, yeah, I'd say limiting reactant are probably the hardest, only because they take the longest and there's multiple steps to them.
Okay, all right, thank you.
Can you also review number 14 for Dr. Altimos?
Yep. Ivan, yes, I'm hoping to post this by 3 o'clock, depending when I get the Zoom link back with the recording. All right, so for question 14, you said 14, right?
Yes.
So for question 14, you said you need to prepare a 0.0482 molar solution of chloride ions with the volume of that many milliliters. What mass in grams of zinc chloride will you need to prepare this solution? Okay, and for all of your questions for short answer, they will always be the answer choice in the box that you're going to put it in. So just make sure your answer choice is in the box on the exam, or else it will not get graded appropriately. Alrighty, so we're given that we want to make this molar solution of chloride ions, and we're given zinc chloride. So if we're given zinc chloride, what is zinc chloride going to do if you dissolve it in water?
Separate
And what does it separate into?
zinc ion and chloride ions.
Good. And how many chloride ions?
2 of them, right?
Okay, so all of this is going to be aqueous. Okay, so you have zinc chloride separating to zinc plus and 2 chlorine ions. So we're given molarity and we're given volume. How does that help us in this question?
You can find the moles.
Yep, I think you both started to say it. But we can use our molarity and our volume to find the moles of chloride ions, right? We want this much. We want 0.0482 molar. which is equal to 0.0482 moles over liter, right? That's what molarity stands for. And we have a volume of 375 milliliters. So how do we get to moles? What do we multiply by?
By the volume given.
Can we use the direct volume?
Molarity times molarity times the volume to get the moles.
Oh.
But you need to convert it to liters.
There we go. Yep, that's what I'm looking for. So it's given to us in 375 milliliters, but molarity is in moles over liter. So, right, so we need to make sure that this is 0.375 liters before we do anything with it. Okay, so this is saying that we have 0.018075 moles of chloride ions in solution. Now what do we do? What is
Yeah,
our
multimole ratio. So you
Yep.
need to multiply it by 1/2.
perfect, right? So we'll have for every 2 moles of chlorine ions, what 1 molar ratio we're using? What goes on top? We have 1 mole of what?
Zinc chloride.
Zinc chloride. And if we're in moles of zinc chloride, do we get to what mass in grams of zinc chloride we need?
You need to do multiply by 136.29.
Beautiful. So I got 1.23 grams of zinc chloride. Now just put this here.
Could you
Any
do
questions?
an ionic equation problem, please?
The net ionic equation problem?
Sure.
Yep. Someone asked about question 15, so I'm gonna do question 15 first, and then I'll do a net ionic equation problem.
Okay.
Zachary, yes, yep, these get partial credit. So let's say you didn't do the molar ratio properly, that's probably gonna be, 1 point, 2 points, half a point off, depending on how much this is worth. Or you didn't convert your answer from milliliters to liters, right? And then that would be some points off. But that's all based off of the rubric that Dr. Altmos will give me to grade by. But yes, you can get partial credit. Okay. Any other questions on 14 before we move on? Does that help the person that asked it? Okay. Okay. So question 15, we have using the balanced chemical equation below, what is the actual yield in grams of O2 when this many grams of that reactant decomposes and the percent yield is 81.4%. Okay, so we have percent yield. What is our equation for percent yield?
Actual over theoretical times 100.
Good. We have actual over theoretical times 100. We're looking for the actual yield. So we're saying that we have 81.4%. It's going to be our percent yield. Actual is our X. Theoretical, we have to find, and we'll multiply it by 100. Okay, so that's what we're looking for, right? We need to find this last piece of our theoretical yield for our equation. We're given 27.4 grams of calcium chlorate, potassium chlorate, excuse me. If we have the actual yield that we're looking for, what do we need to do to this 27.4 grams of potassium chlorate?
Do we convert to moles, then do the multiple ratio?
Beautiful. Yep, we're going to convert it to moles. And then we could do the multimole ratio, saying that for every 2 moles of potassium chlorate, we have 3 moles of oxygen. It's asking for our actual yield in grams. So what's the last thing that we should do?
Convert to grams.
Yeah, we can convert to grams all in one shot. So for every 1 mole of O2, we have 32.00 grams of O2. So I end up that our answer here gets us 10.73 grams of O2. What is that 10.73 grams of O2?
Our theoretical.
This is our theoretical yield. Right, we're saying if 27.4 grams completely decomposed, then we would end up with 10.73 grams of oxygen. But we're saying that this yield is only 81.4%. So how do we solve for our actual yield?
Divide by 100.
Good. Yep, so we can take 81.4 x over 10.73 times 100. We're going to divide by 100. And then we can multiply by 10.73. So we get that x is equal to 8.73 grams. Yep.
Do we have to round to the nearest 10th decimal on the exam?
So based off of this question, how many sig figs do we need?
Three.
We need 3 because we have 3 from our 27.4 in our grams of potassium chlorate, and our percent yield is given in 81.4%. So both of those have 3 sig figs. So you would round to 3 sig figs here, and it's asking for correct sig figures in your question.
So for work converted from 81.4 to 814, are you just removing the times 100 on the right side?
Yes, I am. Yep.
So I have a question because I was doing the homework and maybe it's a different way to solve it, but couldn't you like also solve for the theoretical of KCIO3, then convert that 2 moles of KCl3 and then 2 moles of O2, or would that not work?
I don't think you want to find the theoretical yield for that. I mean, I guess maybe. Right, if you took 81.4% of 27.4 grams. I feel like probably that would work, but that's not the conventional way to solve it. If you do it that way and you get the same answer, that's great. Maybe check it one more time to make sure that it works in a different question. But I would stick to the idea where you're going to find your product first and how much grams that produces, and then divide that, and then like take 81.4% of that. That would be my best option as a foolproof method. I've just never done it the way that you said, so I don't want to confidently give you an answer if it's not going to work. Okay.
For theoretical and actual yield, is it always going to be in grams?
No,
Or-
you could solve for it in molarity, in moles, in any units you want, depending on what it comes out to. But in this case, because our answer was asked for in grams, then that's why we converted it all the way to grams. Okay, someone asked for a net ionic equation problem, so we'll do question 13. So it says, write the net ionic equation for the gas formation reaction below and select all of the spectator ions. So we're given magnesium magnesium carbonate, hydrochloric acid, and then we get magnesium chloride, water, and gas, and CO2 gas. So if we're going to write out our net ionic equation, what can we do to magnesium carbonate?
Leave it the same because it's a solid.
Perfect. Yep, this is going to stay MgCO3 solid. What can we do to HCl? It can be split. Yep, this is 2H plus aqueous into Cl minus aqueous. Right, because there's a 2 in front of that HCl. What can we do to magnesium chloride?
You could separate that into Mg plus Cl.
Right, we could do this Mg 2 plus aqueous, and again 2 Cl minus aqueous. What can we do to water?
It can't be split.
Can't be split. That stays water. What can we do to carbon dioxide gas?
Can't be split either.
S cannot be split either, so that's going to stay as carbon dioxide gas. So looking at our net ionic equation, what looks the same on both the left and right hand side of the equation?
Chloride.
Chloride is the only one that looks exactly the same. And so in this case, this can cancel out and this becomes our spectator ion.
And how do you know which ones you can split up again?
If it's aqueous, then it can split up. If it's not aqueous, then it can't. Does that help with question 13 and net ionic equations?
Yes. So you're canceling out the chlorine because it's not reacting, right?
Yes, right. It's just kind of hanging out in solution. It's not actually doing anything of importance.
All right. Thank you.
Yep. Okay, question 12. How many milliliters of 0.225 HCl is needed to titrate 30 mils of 0.475 molar barium hydroxide to the equivalence point? Okay, so we're given HCl and barium hydroxide. First question I'll ask you is what happens at the equivalence point?
The moles are equal.
And moles of what are equal?
Of the acid and the base.
Moles of acid and base are equal. Okay. The next thing I would suggest you do is write out your equation. So you have HCl and you have barium hydroxide. What does that form?
Water and barium chloride.
Good. Do we need anything on that barium chloride?
Is it a 2?
It is. Great. Okay, is our equation balanced?
No.
Nope. How to
The
balance it?
chloride, the hydrogen chloride needs a 2.
Yep. Anything else?
Looks right to me. No.
We're close. We
Is
just
it
needed two.
H2O missing a 2?
Yep. We just needed 2 in front of our H2O. Yep. So now we have a balanced reaction here. Okay. So you can do this in 2 ways. There is the MA BA divided by A is equal to MB VB divided by B, where A is your acid and then B is your base. And the little a on the bottom is the coefficient in front of your acid and base. You can do it that way, or you can do regular dimensional analysis in order to figure out your molar ratio and whatnot. So if you're going to do dimensional analysis, you have 0.475 moles, I'm sorry, molarity of barium hydroxide. And we need to get to moles. So you multiply this by 0.030 liters. So we get this many moles of barium hydroxide. We know that our molar ratio is that for every 1 mole of barium hydroxide, we need 1 mole of, or not 1 mole, excuse me, 2 moles of HCl. So that's that many moles of HCl. And then in order to find volume, we would say that we have 0.225 moles over liter is equal to 0.285 moles divided by X, because we don't know what that volume is. And we end up with 126.7 milliliters HCl. How many sig figs do we need to go to here?
Three.
Yep. So what's going to be our final answer?
127 milliliters.
127 milliliters. Okay. We can also check this by doing the other equation that I talked about. So our molarity of our acid is 0.225. We don't know our volume, and we know that our coefficient of our acid is 2. For our base, we have 0.475. we have 30.0 mils, and our coefficient is 1. So if we solve for this, we still end up with X equaling 127 mils. So that checks out.
And both of them are acceptable for a free response question.
Yep, if I would just show your equation, if you're going to use the MAVA, just make sure you show your equation. That's as a rule of thumb too. If you're going to use an equation, always show it before you plug your numbers in.
All right, thank you.
It's like the percent yield question earlier. Make sure you show that percent yield is equal to actual over theoretical times 100. I'm assuming these are all for Altmos's exam. Okay, so for question 3, we have if you add 15 mils of 1.25 molar copper chloride solution to a 50 ml volumetric flask, and then fill the flask with the line with water, what will the concentration of the diluted solution be? So this one is very similar to the one that we just had, except this is a serial dilution, and a little bit less complicated. So if you're doing this, if whenever you see diluted or you're taking a stock solution, any sort of that verbiage, you want to think of M1V1 equal to M2V2. And in this case, right, this will always be so that you have a big number, and this is going to be a small number, so that your molarity ends up as a small number, and your volume ends up as a big number. Okay. So if we were to label 15 mils, is that going to be what variable in our equation is that going to be?
The start one.
I think starting volume is what I heard in volume 1. So yes, V1. What about 1.25 molar?
M1.
Good. And what about 50 mils?
V2.
That's going to be V2, right? So then you can just plug and chug into what you have. So for M1, we have 1.25 molar. For volume, we have 15.0 liters, or sorry, liters. Milliliters. Do we need to change that to liters?
No.
Nope. And then we have our X because we don't know what our concentration is going to be. And then we have 50.0 mils for our volume. So we end up with X equaling 0.375 molar. Now, does this make sense? Does this answer going down for our concentration make sense?
Yes, because
Yes,
the
it does.
volume's increasing.
Good. Our volume's increasing, so our total concentration is going to go down, right? So we expect a diluted solution, right? Or a less concentrated solution. So this makes sense. So C is correct.
I have a quick question. Going back to the equation that you used for number 12, could you explain just the parts of it, what you plug in on that one? Thank you.
Like the one in red down here.
Yes.
So when we talk about MAVA over A is equal to MBVB over B, it's the same thing that we just did with M1V1 equal to M2V2. But this time, right, sometimes you have a diprotic acid or a diprotic base. And so this coefficient here is the or this letter here is the coefficient in front of either your acid or your base. So in our equation that we wrote, we have a 2 in front of our hydrochloric acid. So that now becomes little a. So little a here is that 2 value, which is what you see here. For our barium hydroxide, we're saying that this is a 1. So barium hydroxide becomes 1 in our equation. This is to show that for every 1 mole of barium hydroxide you have, you need 2 moles of hydrochloric acid in order to have a 1-to-1 ratio, right? Using those coefficients now allows you to have a 1-to-1 ratio. Then the mass, so then the molarity and the volume for your acid and molarity and volume for your base follows the same rules as your M1V1 equal to M2V2.
I see. Makes sense. Thank you.
Does that help a little bit?
For this question, how do you know the products of the reaction?
So what is, right, we have hydrochloric acid and we have barium hydroxide. And we're also given the word titration. So what is usually used in a titration?
Water.
Water is a product. Yep, so we see that. And then what else is used in a titration? Like what do we
An
call
acid and a base.
it? Yep, we have an acid and we have a base. And so whenever you're going to titrate something, you're going to be creating water and a salt. And so your salt is that barium chloride. If you look at your reaction, so that it's HCl plus barium hydroxide 2. If you look at it that way, now you can kind of see that this is also a double displacement where your H and OH are going to bind, and then your chlorine and your barium are going to bind. And that's why you come up with your 2 products. Does that help that one?
Yeah, that's good.
Yep. Okay, I think I have time for one more question as we're nearing 2 o'clock. Yep, so for this one, for 5 here, we have gallium, number 31 in the periodic table, has 2 naturally occurring isotopes, these 2 here. Based on the table below, what is the mass in AMU of gallium? So your percent abundance question, I'm just going to talk you how to do this, right? Your percent abundance is mass of isotope times percent of isotope plus the mass of your isotope times the percent of your isotope. This is mass of isotope 1, mass of isotope 1, mass of isotope 2, 2, right? Stuff like that. So do we know, I'm sorry, when we talk, this is not percent abundance. This is average atomic mass. Sorry about that. Right, your average atomic mass. Where can we find our average atomic mass?
Periodic table.
Yep, this comes from the periodic table. So in this case, you can look at this up from periodic table. Our mass of isotope 1, which is mass 69. We don't know, so that's going to be our X. And our isotope percentage is going to be 0.6011, right? You want to convert that into a decimal. We also know our mass of 71 is 70.9246, and our percentage is 0.3989. So if you look up the molecular weight of gallium from your periodic table, then the only thing you don't know is X, and you can solve from there. Does that help with number 5?
Could you explain what the PT stands for again? Is that the average atomic mass?
The PT.
Yeah, I'm just a little confused on what that stands
Yep.
for. I don't know if it cut out or something.
Sorry. Yeah, sorry. That just means that you get this from the periodic table. You find that from the periodic table.
Oh, I see. Thank you.
Yep.
Will there be a time where we have to use where they don't give us the mass where it's just x and then the other one will be x minus 1 or 1 minus x?
Yep. You could definitely ask that type of question.
Will this be posted on our Canvas?
Yeah, I'll make an announcement that the recording is posted, but it'll be under that office hours tabs again. Okay, so with that, it is 2:02. I'll let y'all go back to your Sunday activities. If you have any questions between now and your exam, please just send me an email. I'll be happy to respond to them. Hopefully maybe tonight, maybe tomorrow morning at the latest. And good luck studying. Make sure you get a good night's rest and just make sure you work diligently and everything's going to be okay. And I'll have this hopefully posted by 3 o'clock.
Thank you.
Yeah, thanks so much. Have a great rest of your weekend.
Thank you. Have a good day.
Thanks for coming.
Thank you.
Thank you very much.
Thank you very much. Have a good one.
Bye.